Have you ever looked up at the night sky and felt a sense of awe and wonder? The universe is a vast and mysterious place, full of incredible objects and phenomena. As we gaze at the stars, we can't help but ask ourselves profound questions about time, space, and our place in the grand scheme of things. Imagine for a moment that we could travel to distant stars. Would time pass differently for us out there in the cosmos? Would we age at the same rate as people back on Earth? These questions might seem like science fiction, but they lie at the heart of one of the most revolutionary scientific theories ever conceived: Einstein's theory of relativity. For centuries, scientists believed that time and space were absolute and unchanging. Sir Isaac Newton, a brilliant mind of the 17th century, described a universe governed by precise laws. In Newton's universe, time ticked away like a perfectly calibrated clock, the same for everyone, everywhere. Space too seemed absolute, a vast and unchanging stage upon which the celestial dance of planets and stars unfolded. This view of the cosmos, orderly and predictable, reigned supreme for centuries. However, at the dawn of the 20th century, a young physicist named Albert Einstein would challenge these long-held assumptions and change our understanding of the universe forever. Albert Einstein, with his wild hair and piercing gaze, was not afraid to challenge conventional wisdom. He dared to imagine a universe where time and space were not rigid and absolute, but rather intertwined, forming a flexible fabric that could be stretched and warped. Einstein called this revolutionary concept spacetime. Imagine a sheet of rubber stretched taut. This sheet represents spacetime. Now, if you place a heavy object like a bowling ball in the center of the sheet, what happens? The sheet curves downward, creating a dip around the heavy object. This, Einstein realized, is how gravity works in the fabric of space-time. Massive objects like stars and planets create warps in space-time, much like the bowling ball on the rubber sheet. These warps are what we experience as gravity. It's not that objects are magically attracted to each other. Instead, they are simply following the curves in the fabric of space-time created by the presence of other objects. Imagine Earth orbiting the Sun. It's not that Earth is being pulled towards the Sun by an invisible force. Instead, Earth is simply following the curvature of space-time created by the Sun's massive presence. This cosmic dance between massive objects and the fabric of space-time is a fundamental concept in Einstein's theory of general relativity. One of the most intriguing consequences of Einstein's theory of relativity is time dilation. Time, it turns out, is not the same for everyone. It's affected by both speed and gravity. Now, to understand this mind-boggling concept, let's imagine a pair of twins, one who stays on Earth and the other who embarks on a high-speed journey through space. The twin who travels at incredibly high speeds will experience time passing more slowly than the twin who remains on Earth. This means that when the spacefaring twin returns to Earth, they will be younger than their Earthbound sibling. This phenomenon, known as the twin paradox, highlights the relative nature of time. The idea that time is relative might sound like something out of a science fiction novel, but it has been confirmed through numerous experiments. One of the most compelling pieces of evidence comes from atomic clocks, the most accurate timekeepers ever invented. Scientists have flown atomic clocks on airplanes and even sent them into orbit around Earth. These experiments have shown that the clocks on the fast-moving airplanes and satellites tick slightly slower than their counterparts on the ground, just as Einstein's theory predicts. The effects of time dilation become even more pronounced in the presence of extremely massive objects like neutron stars and black holes. These celestial behemoths warp space-time to such an extreme degree that time near their surfaces slows down dramatically. Imagine a spacecraft venturing close to a black hole. As it approaches the black hole's event horizon, the point of no return, time would slow down to a crawl for the spacecraft, while time would continue to flow normally for observers far away. This warping of time near massive objects is one of the most mind-boggling predictions of Einstein's theory of relativity. Einstein's theory of relativity is not just a theoretical curiosity. It has profound implications for our understanding of the universe and our place within it. It has also led to practical applications that have revolutionized our technological capabilities. For instance, the Global Positioning System, or GPS, which we rely on for navigation, would not be possible without taking into account the effects of time dilation. GPS satellites orbit Earth at high speeds, and their clocks run slightly slower than clocks on the ground. Engineers must account for this time difference to ensure the accuracy of GPS location data. Einstein's theory of relativity revolutionized our understanding of space, time, and gravity, but it also raised many new questions. Scientists today are still grappling with the implications of Einstein's work, seeking to unify his theory of relativity with quantum mechanics, another pillar of modern physics. The quest to understand the universe is an ongoing journey, and Einstein's legacy continues to inspire generations of scientists. As we delve deeper into the mysteries of the cosmos, we are constantly reminded of the vastness of the unknown and the power of human curiosity to unravel the secrets of the universe.